In today's video, we'll be talking about piecewise functions. To begin, we'll review the library of basic functions and use those graphs to build more complicated graphs known as piecewise functions. Let's get started. So we want to recall that in previous classes, we've already studied the graphs of some basic functions. For example, y equals x squared, our parabola. Y equals x cubed, our snake graph. Y equals the square root of x, half of a parabola on its side. Y equals the absolute value of x, our absolute value v-shaped function. And you can click on the link in the notes as well to see a list of the other library of function graphs that you should have studied in previous classes. But today I want to remind you that if we have a function, its graph must pass the vertical line test. See here. So we want to pass our vertical line test. And as long as a graph passes a vertical line test, we still can call it a function. Now, one type of function that is made up of two or more pieces and is defined by certain restrictions on its domain is called a piecewise function. So for example, let's consider the function f of x equals negative x whenever x is less than 1. And f of x equals the square root of x minus 1 plus 1 whenever x is greater than or equal to 1. So the very first thing you want to do is notice what types of graphs we're talking about. For example, in the first piece, I notice that I have a line. In fact, that line, it is familiar to us, I hope, because we remember that a line like this could be written as y equals mx plus b, where that line y equals mx plus b tells us our slope. In this case, our slope is negative 1. And it tells us our y-intercept, which in this case is 0. Now, the interesting thing about that piece of our functions graph is that that line is only allowed to exist whenever x is less than 1. So what that means is, if I were to graph this line normally, I would start at my y-intercept of 0, but is 0 even in my restricted domain? In this case, we would say, well, yes, it would be. It would be in our restricted domain because x is less than 1 would include all of these values starting at 1 and to the left of it. So what we want to do is actually put our point 0 for our y-intercept, which would be right here. Okay? And then we want to use our slope to go down 1 and right 1 to get to our next location. So if from that point of 1, let me change the color here so you can better see this. Let's see, how about blue? Okay. So starting at our y-intercept of 0 there, okay. What we want to do is use our slope of rise over run, so go down 1 and right 1 to get to our next location. So if I had gone down 1 and right 1, we would have been at the point 1, negative 1. Now that technically is not allowed for an x value. So we would have an open circle there at that location. So we indicate that with an open circle at the point 1, negative 1. Now in the other direction though, we could have also used our slope of negative 1 to have gone up 1 and left 1 unit. So if we had traveled from the y-intercept and gone up 1 and left 1, we'd be somewhere around here. And we could continue that progression, going up 1, left 1, up 1, left 1, continuously, because for a line, your slope remains constant, your rate of change remains constant. And so eventually we would have enough information to sketch that part of the line, looking something like this. Now that's just part of the function. We know that the second piece of the function is for those values which are starting at x equals 1 and x values bigger than 1. So in order to do that part of the graph, we would need to talk about what that graph looks like. So let me switch to a different color there. How about red? I think I picked red. Let's see. Yeah, here's red. Maybe orange. Orange or red. We'll see what we get. Okay, so for this graph right here, we need to remember what that graph is. Okay? That's definitely not a line because it's not linear in the sense that we don't have a degree, a highest power of 1. Instead, we have a degree of 1/2 because a square root, if you remember, is really a highest power of 1/2. So what did that square root function look like? And this is where we might need to go back and review our library of functions if you don't remember that graph. What we remember, hopefully, is that if we have y equals the square root of x, that refers to our square root graph, which originally has some key points, if we think about those, at 0, 0, because the square root of 0 is 0, at 1, 1, because the square root of 1 is 1, and at 4, 2, because the square root of 4 is 2. So if we thought about that as our original graph of y equals the square root of x, we could then transform it using the transformations that we see have taken place here. So what transformations have taken place? Well, my initial 3 key points of 0, 0, of 1, 1, and of 4, 2 have now been moved. But how? Let's take a look. I'll switch colors again if possible here. Let's switch maybe to violet, see if that works for us. Okay, so in order to move it, let's see what we have to do. We notice that this negative 1 inside the square root function is a horizontal shift to the left or to the right. And we need to remember from our library of functions that we've studied in the past that when a negative or a positive number is being added inside of the function, it's counterintuitive. So instead of moving left 1, it's actually moving to the right 1. So to move left or right, which values would be affected? Well, the 0 here, our x value, would be affected. So instead of 0, 0, that x value now is going to be at 0 plus 1, which is 1. Now what about the other transformation that we see taking place? For example, the one that's being added on at the end of the equation. Well, that's a vertical shift. It's adding 1 to all of our y values, So if we look at our 0 here for that point 0, 0, that will now become a 1. So we have a new point for this graph, this part of the graph, and that would be at 1, 1. So for example, the point 0, 0, which was at the origin, would have moved to the right 1 and up 1, which makes sense. It's now living at 1, 1. Okay. What about the point that was originally 1, 1? Well, again, if you move that point up 1 and right 1, you would get 2, 2, wouldn't you? By adding 1 to both the x value and the y value. So that point, which was originally at 1, 1, is now at 2, 2. So 2 right and 2 up. And so we end up getting a graph that looks something like this. It's shifting up and it's shifting right. So if we put our new points on the graph, we have 1, 1, we have 2, 2. The third point, instead of 4, 2, should be 5, 3 as well. So if we put those 3 points on our graph, the only thing we have to watch out for now is, are we satisfying the domain? So what does that mean? This graph can only exist when x is greater than or equal to 1. Well, if I look at those 3 points, we are in luck because my lowest x value that I had was 1, 1, right? The point 1, 1, which means that point does exist. If, however, you have a point which does not exist, you would want to go up to a next highest point, a point where x is greater than 1 or equal to 1. So let's plot our points here. At 1, we're at 1, so that's going to be somewhere around here. At 2, we're at 2, so an x of 2 is a y of 2. So let's see, somewhere around here. And at x equals 5, we should be at y equals 3. At x equals 5, we should be at y equals 3, so somewhere around here. So our graph is looking something like that. It should look like half a parabola on its side. And we notice what's happening. It's kind of hard to see in my picture. I apologize for that. But at x equals 1, there is a break in our graph. There is a break. So we have an actual location at x equals 1 with the y value 1. But at x equals 1, where we would have had a y value of negative 1 for our blue line, that's an open circle because that was not allowed to exist. Only values to the left of it. So we would actually say this is a function. It's a piecewise function, but it is discontinuous. And when you get to calculus, you'll learn about discontinuities. This particular type is called a jump discontinuity, since there's a gap between those points at x equals 1. Okay, so let's move on to another example. Let's see if we can clear this one out and move on to our next example. Okay, so before we begin example 1, I want to remind you that in addition to being able to eventually graph these, which is what we're practicing right now, you might also be asked to give the equation yourself, right? So in this one it says, you must know how to interpret such equations as well as how to write a piecewise functions equation or rule when given when given its graph. So you might have to actually write the rule yourself in the future. Okay, that's what that is saying here. Okay, so let's see our first example here. It says, let g of x equal 2x whenever x is less than 0. Let g of x equal x whenever x is greater than or equal to 0. Now here it's interesting. It doesn't just say to sketch the graph, but it says find g of -1 and g of 0 and g of 1. So what is that? Well, if you remember from your earlier discussion of functions when you first began your algebra experience, we talked about something called function notation. And function notation, whether it's f of x or g of x, it just meant at a certain x value, you should be able to know exactly what the y output is. So if we give you an input like an x in the domain, you can give us an output like a y in the range. So that's what we're doing here. They're saying when they say g of -1, they're telling you when x equals -1, what is the function named g? What is the function's y value? What is its output? Well, you might be confused. Looking at this equation, it almost gives you the idea that you're having two outputs at that x value. But that's not right, because you're actually given a roadmap when you look at this equation. You're told, under this condition, use this piece. Under this condition, use this piece. It's kind of like if you go to the post office and you're trying to pay for shipping a package. It'll tell you if you're trying to ship a package that weighs this much, you pay this. This much, you pay this. Or doing your taxes. If you're in this tax bracket, you pay this tax. Piecewise functions are everywhere in real life. This is just a more theoretical algebra-looking one, but we deal with them all the time. So let's take a look at this example more carefully now. We see the first part, the first piece of the function is y equals 2x. And you'll notice that I keep saying y equals because a function, g of x or f of x, is really your output. That is your y value. Okay, so y equals 2x. Let's take a look at that. So y equals 2x, we need to notice again what type of function is that piece. And again, it's a line. It's a line whose slope is 2, and it's a line whose y-intercept is 0. So with that in mind, I can begin my picture as long as I keep in mind that this graph can only exist, this piece of the graph can only exist for x values less than 0. Okay, so they travel according to this slope only when x is less than 0. So let's begin at the y-intercept of 0, but notice we can't actually exist there, only values less than 0. So I'm going to use it as a sort of a cutoff, a boundary. I'll use an open circle for that reason. So at 0, we would have our y-intercept, but I use an open circle indicating it's a boundary. It's not actually existing there. And then I could use my slope. Now normally my slope, my rise over my run, would mean go up 2 since it's positive and right 1. But if I did that right now, think about this. Would this be a point on this function's piece? No, it can't be, because that would actually bring us to an x value of up to over 1. That's an x value of 1, which is not less than 0. So in the other way, we could say that a slope of 2 is also down 2 and left 1, because that's also equal to 2, isn't it? -2 divided by -1. So if I travel down 2 and left 1, let's see what that would do. Down 2 brings me to a y value of -2, and left 1 gives me an x value of -1. That would be my location. And again, because it's a line, our slope or our rate of change is constant. So we could continue that over and over again to get more and more points on the line if we wanted. Going down 2 again, we would be at -4 and over 1, so something like this. And we can continue going down 2 and over 1. And eventually we have enough to draw that part of the graph. Now for our second piece, we also see a line. Let's take a look with it, maybe a different color here. How about blue, if we can get that? Yeah, I think so. Okay, so we look at our second piece of the graph. Now this piece looks like a line again, a very simple line. It's actually our identity function. And this line has a slope of 1. You don't see the 1, but it's always implied with multiplication there. So that slope is up 1, right 1, or left 1, down 1 as well. And our y-intercept, again, since we don't see a constant, is still at 0. Now something very interesting is about to happen, because if we look at where the function has its change of direction or its change of slope, that happens when x equals 0. That's when we switch pieces. We switch from one piece to the next, right? Now sometimes, like the last example in the previous slide, we actually jump. We have a jump discontinuity from one y value to the next. Other times, we actually fill in the previously open circle because of where the y value lands. So let's take a look at how that works here. Here we have a slope of 1 with a y-intercept of 0, which would mean I would be able to now fill in my point on the origin. So let's do that. So now we filled in that point on the origin. And now we're going to use our slope to go up 1 and right 1. Now, why am I not going left 1 and down 1 like I did last time? You might be thinking. Oh, well, that's because our function is only defined for this piece for x values starting at 0 and to the right of 0. So let's go up 1 and right 1. So if I go up 1 and right 1, somewhere right here at the point 1, 1. If I go up 1 and right 1 again, I'd be at the point like 2, 2. And if I go up 1 and right 1 again, we're going to keep going like 3, 3, 4, 4, etc. And we're going to have a line with a little bit less steepness, okay? So it's not quite as steep as a line whose slope is 2, right? So if you're thinking about roofing, this part of the roof would be safer if you're putting your Christmas lights on your house. The other side, a little bit too steep for my taste. Okay. All right, so now what we've done is we put together two pieces of this function. And interestingly enough, we no longer have a discontinuity because we were lucky enough, in a sense, to actually fill in our previously open circle. Now it's closed. So this is now continuous. They're both piecewise functions, but one is continuous and one is discontinuous. Let's answer the rest of the questions. We've actually done the sketch first, which is fine. Let's answer the first question that they asked us now. What is g of negative 1? Well, I could look at my graph. Again, a sketch is not something I want to depend on, especially if I wasn't using a ruler, right? So let's take a look at the equation instead. This is saying when x is negative 1, what is y? Well, which of those pieces would I use? X is less than negative 1. You're right, it's the first piece. So I would actually use the first piece because that's when x is less than 0. So looking at that first piece, when x is less than 0, I would plug in negative 1 for x. So 2 times negative 1 is negative 2. So what does that mean? That means when x is negative 1, my y value, the output if you will, is negative 2. And that should match with my graph. If I were to go to x equaling negative 1, I should be able to go down and see my y value at negative 2 if I've graphed it correctly. Similarly, they ask us for g of 0 next. And so for g of 0, that's a little trickier because you see 0 in two places, don't you? You see it in two places. You see it over here where we have 2x whenever x is less than 0. You also see it when you have x whenever x is greater than 0. So which one is it, greater than or equal to 0? It would have to be equal to, wouldn't it? And so that would be our second piece. So we would say, what is x? X is 0. So when x is 0, y is x, and the x value there is 0. That also makes sense. If we go back to our graph, when x is 0, y is 0, so that is now a point. The final one they asked us for is g of 1. Similarly, 1 is bigger than 0, so we would use our second piece. So replacing, again, our x value with 1, we would just get 1. So this is saying when we look at our graph, at the x value 1, the y value is also 1. And we should be able to see that if we've sketched it correctly. Okay. All right, now in the next example, I encourage you to pause it and try it on your own, and then join me and see how you did, okay? So let's go ahead and head over to our next example. Let's clear this guy off first. Okay, next example. So again, try this one on your own, and then maybe come back and see how you did. Okay, now that you've tried it on your own, let's take a look together. We have h of x equals 2x plus 4 whenever x is greater than 1. We have h of x is equal to x plus 2 whenever x is less than or equal to 1. So unlike last time where things changed when x was 0, this time things are changing when x equals 1. Similar to last time where both equations were representing lines, also again, both equations are representing lines here. So whenever I think lines, I think what is my slope and what is my y-intercept. So let's take a look. For our first line, our slope is 2, and our y-intercept is 4, which would mean then that I would start at a y-intercept of 4 as long as it's defined. So let's think about this. We're only allowed to exist in this way when x is greater than 1. Well, would the y-intercept of the point 0, 4 qualify? No, it wouldn't, would it? So instead, what I would encourage you to do is keep the slope as your guiding principle here and find a point that does qualify. You could start with the y-intercept, but you'll have to erase part of that line. And that's a little bit traumatic for some of you if you don't have an eraser at hand. You might mess up your graph. So I would recommend keep in mind where the change is happening. So my change is happening at the x value of 1, isn't it? That's where I changed from one piece to another. So I'm going to say, okay, what would have happened, for example, if x was 1? Even though we know I have to be bigger than 1, let's just hypothetically, let's let x be 1 for a moment in this first piece. Well, then wouldn't we have 2 times 1, which is 2, plus 4? And 2 plus 4 is 6. So we would have had the point when x is 1, y is 6 for the first piece. I'm going to put that on my graph as an open circle, as a boundary point. So when x is 1, I would have been at 6. So let's see, that's 2 here. Let's see, 1, 2, oops, erase that guy. Okay, back to my pen. 2 would have been up here at 6. So I'm going to put an open circle there, if you will. And then from there, I would have used my slope to go up 2 rather. So that's my slope, so 2 over 1, up 2 and right 1. So from there, if I went up 2, I'd be at a y value of 8, and then over 1, so something like this. You could have gone up 2 again, being at a y value of 10, and over 1. And eventually, we have something that resembles a line with a slope of 2, hopefully. So there's one piece of the graph. And again, why did I start at the x value 1, potentially? Because that's where the change happened, didn't it? Again, if you had started at the y-intercept 0, 4, you would have had a piece of the graph that's not actually allowed to exist. So that could be more annoying than it's worth. Okay, let's look at our second piece. Let me maybe switch colors to blue. Okay, for the second piece, it's also a line, we notice. But we notice that this line is when x is less than or equal to 1. So I would begin with, what is my slope? My slope here is the coefficient of x, which is 1. And what is my y-intercept? Yeah, it's 2. So with that in mind, I say to myself, can I graph my y-intercept? Does it exist in this case? Well, that would be at 0, 2, and 0 is an x value less than 1 or equal to 1. So yes, I would actually start this time at my y-intercept. So 0, 2 means somewhere around here. That point does exist. Now you might be thinking, but what about at 1? If you are thinking that way, that's good, because we are going to want to get as close to 1, and in this case, even equal to 1, aren't we? So if you wanted to, you could find out what happens when x is 1. Well, plugging in 1, we are actually asked that in our question here, find h of 1, right? Plugging in 1 to that second piece, we would get 1 plus 2, which is 3. So we could actually answer that question and plot it at the same time here. When x is 1, our y value should be at 3. So that's around here. Okay. And so what should happen is, if my graph was a little bit better, I apologize, that point should be directly underneath the point above it, because we had a point as our boundary that was at the location of 1, 6, right? So right below it should be our point that we just graphed, and that would be at 1, 3. Okay, so that's called a jump discontinuity. If I had continued going down with that slope, again going down 1 unit and left 1 unit, continue that way, you'll end up getting your line that looks something like this. So this line again is not quite as steep as the first piece, and this time we have a jump discontinuity when x is 1. Okay, we can answer the other questions easily using the equations. H of negative 3, well, that would be our second piece again. Negative 3 replacing x with negative 3 here. So replacing this x value with a negative 3. Negative 3 plus 2 is negative 1. So we should check in our graph that that makes sense when we actually compare our sketch with these answers. If you do it correctly with your ruler and your graph paper, they should match up nicely. When you put an input of negative 3, you should get the output of negative 1. We already answered h of 1. When you have an input of 1, we get the output of 3. And finally, for h of 3, when we put an input of 3, which piece would that be? So if x is 3, well, yeah, that would be an x value greater than 1. That's the first piece. So we put it into our first piece this time. 2 times 3 is 6. And adding 4 to 6, we would get 10, following our order of operations there. So what we're saying there is that when x is 3, when our input is 3, y is 10. Our output is 10. Now there's one other question here that I've posed to us, And part C, I said, after we sketch, could you find the domain and the range? So let's remind ourselves what those principles or those terms meant. Domain was just the set of all x values that are legal, right? Which x values is your function allowed to put into the system? And so in this case, it looks like all x values, right? Because for the first piece, it's the x values greater than 1, and for the second piece, it's the x values at 1 or below. So every x value is potentially allowed. So we would say in interval notation, from negative infinity to positive infinity, with parentheses because we can't reach infinities, right? That would be our domain. Our range, on the other hand, is the set of all y values that could potentially be reached by our function, if we remember that correctly. Now we can see from the graph what's happening. The blue part, or the second piece here, is allowed to keep going down following its slope, 1 over 1. It's allowed to keep going down as we go to the left forever. So if you're allowed to keep going down without any restriction, then your range has a minimum of negative infinity because you're allowed to go down forever. But here's what happens in this graph, unlike the last one where they joined up. In this graph, we have a jump. So we have a jump at x equals 1. We notice that at x equals 1, the blue graph had a y value of 3. But then the red graph jumped up to the y value of 6, but didn't exist there. It was a boundary. So if you jumped up from 3 to 6, there are some values for y that we never reach. So we can reach any value until we get to 3, meaning we can put a bracket there, including the 3. Or other values, and the way we represent or usually is that symbol that looks like a big U. It means union. Or we would allowed to have any y value that is greater than 6. So that would be 6 toward infinity because we go up forever. But that 6 would have a parenthesis this time. Why a parenthesis? Well, remember, parentheses mean you are not actually allowed to have that value, that endpoint. So it's values which are greater than 6, but not 6 itself. So that is important. All right. So I think at this point we have a couple more to practice here. Let's take a look. Again, you're welcome to pause it anytime you like to practice on your own. Okay, so our next example, things are getting a little more difficult now. We have to remember those functions we've studied in the past. Our first function that we see here, or piece of our function rather, is f of x equals 2x squared whenever x is greater than or equal to 1. So whenever x is greater than or equal to 1, we have a certain type of function and it's not a line. How do I know it's not a line? Because its highest power is not 1, but 2. We're going to be studying these polynomial functions more in our next section in future days. But for now, we should remember from previous experiences of library of functions, graphs, that whenever I have a degree 2 polynomial, that graph should be coming right up in your memory as a parabola. Okay? Those parabolas can be opening up or down. So in this case, if we remember that if I have a graph y equals x to the second power, that's one of my basic parabolas I should always remember. And it had 3 easy points that I could keep in my mind all the time. Whenever x equals negative 1, I have a y value of, well, negative 1 times negative 1, it's positive 1. So I have a key point when x is negative 1 at positive 1 for y. Similarly, whenever x is 0, 0 squared is 0, so we have a point at 0, 0. And whenever x is 1, 1 squared is 1, so we would have a point at 1, 1. And so we would remember, hopefully, that the way this graph keeps growing, it's not going to be linear in those pieces, but rather it's going to curve upward and start growing faster and faster. Because when you get to x equals 2, for example, your y value is not at 2, it's at 4, because 2 squared is 4. When you get to x equals 3, your y value is not at 3, but at 2 to the third power, which is going to be 8, right? So we're going to have it grow pretty quickly. Or I should have said not 2 to the third power, sorry, but 3 to the second power, is 9. Sorry, it's still growing quickly. So it's going to actually look something like this. Okay, so we have this parabola that's opening upward. That's what we keep in our mind with our 3 key points at negative 1, 1, 0, 0, and at 1, 1. And you can keep more in your mind, just write them out. Plug in an x, get your y. Okay, what's going on to this graph though? Well, the transformation this time is multiplying x squared by 2. That was called a vertical stretch. It's not a vertical shrink because it's a number greater than 1. It's actually growing faster now. In other words, its y values are growing twice as fast. So I can simply get my new points. I can switch colors perhaps to demonstrate that. Instead of my y value at 1, my y value is now at twice as fast, 2 times 1, which is 2. So this would be at negative 1, 2. 0, 0, if you multiply the y value 0, well, 0 times anything is still 0. That one's kind of boring. So that point stays at 0, 0, the origin. But what about when the y value 1 gets multiplied by 2? Well, that's going to get multiplied by 2 to become 2. So we'd get 1, 2. So this graph, this would be the parabola that would actually be growing faster than last time. So if this is 2 now, for example, it's something like this. The parabola has been stretched vertically, if we remember that correctly. So this graph is growing a little bit faster, and had the coefficient of x squared been a number like 1/2, less than 1, it would have grown slower. It would have been what we call a shrink instead of a stretch. Okay, so what's happening in our piecewise function now that we've reminded ourselves of what kind of piece that was, a parabola? Well, we're only allowed to be that parabola when x is greater than or equal to 1. So that means part of that graph is not important to me, right? The only part that's important to me is when x is greater than 1 or equal to 1. So if I were to look at 1 here, for example, I think these are going by 2s. That's my mistake last time. Yes. So if I'm saying I'm going to start at 1, that would be like right here, okay? So at 1 itself, what would our point be? Well, we talked about it. It would be at 2, wouldn't it? So 1 was at 2. X is 1, y is at 2. So we're going to go up to 2 there. Okay? That point's allowed. But notice which points are not allowed. Any point to the left of that. What would the next point have been? Well, you could pick another point since we aren't quite there with our library of points there. What about when x is equal to 2? Well, we could say, well, 2 gets squared, doesn't it? Because the equation is 2x squared. So if you put 2 in as your x value, what I'm saying here is if you put 2 in, I should say f of x, shouldn't I? Be consistent here. Okay. So if you put 2 into your function, what is your y value? What is your output? So that's 2 squared, which is 4, and 4 times 2, which is 8. So that is shooting up quite quickly. When x is equal to 2, we should have a y value of 8, which I think is right there. Okay. So this graph is shooting up quite quickly, especially since I graphed it by 2s. Okay. So it shouldn't be curving, but it should just be going up quickly. Okay. Not a line, but a curve. Half of a parabola, but not even quite half, just the part starting right there. So this is the part we're actually seeing. Okay, so we have that part of the graph done. Let's talk about the other part. The other second piece, maybe switch to brown here. The second piece is a different type of function that's not quite as popular perhaps. Actually, let me switch to a color you can see. How about black? No, I don't like black. Let's do a different color. I think purple worked last time. Let's try that. Okay, so in this case, this graph is the absolute value function. And if you remember from the absolute value function, y equals the absolute value of x, the key points for that graph, they kind of look like the key points for the parabola, but the growth is different. Instead of growing in a curvy manner quickly, the key points were when x is negative 1, y is still at 1, because the absolute value of negative 1 is 1. When x is 0, y is still at 0, because the absolute value of 0 is still 0. When x is 1, the absolute value of 1 is 1, so your y value is 1. So so far, it looks like the same key points as our parabola, doesn't it? But the difference was that the growth is linear, right? They continue growing that way, like lines, like 2 separate lines put together. Basically a piecewise function of 2 lines with 1 negative and 1 positive slope. And the reason for that is we're not squaring any x values. We're simply making them positive to get our new y value. So your y values always stay positive and they grow in that nice linear progression, like a V shape. But when is this graph allowed to exist? According to our function here, it's only allowed to exist when x is less than 1. When x is less than 1. So again, last time for the first piece, we said starting at x equals 1 is where we were allowed to exist, and that was at a y value of 2. This time, we're allowed to start x values that are less than 1. So we ask ourselves, at that cutoff, when things are changing, where would it have been? Because that will be my open circle. So if I had let x equal 1, that would have been at the point 1, 1, wouldn't it? So I would go to 1, 1, which is around here, and I would put my open circle. It doesn't quite look open because I'm drawing it too close together here. Let's see if I can fix that. Okay. But it should be a nice open circle. Make it very thin here. Right there. So I'll just write it. That's open. Okay. So that's a nice open circle. And then from there, we would go to our next point to the left, which would have been at 0, 0. So let's find that. 0, 0 would have been right here. And then from there, we would have gone to our next left point, negative 1, 1. So negative 1, 1 up here. And so what we have is part of that V-shaped graph. Oops, I apologize. My graphing skills are not great today. Okay, so we should have part of that V-shaped graph. Not quite all of it, but we have the left part of it until we get to the origin, and then we go up, approaching the point 1, 1, but it's an open circle. That's when we have the discontinuity. If I were to just draw a sketch to the side so you can better see what's going on, you can't really see that, sorry. I'll fix it for you. One moment. Okay, if I were to draw a simple sketch to the side in a color you can see, I think you can see blue pretty well. Let's try that. That's okay. So basic idea, you should have something that looks like this until you get to a point with an open circle. And then from there, you should be shooting up one right above it in a nice curvy manner. So something like that is going on. Okay. Again, that's a jump discontinuity. It's still a piecewise function, but it's a jump discontinuity because we didn't actually meet back up again at that location x equals 1. As far as domain and range is concerned, well, for the domain, do all of the x values potentially work? Are there any restrictions, any x values which are not allowed? No, right? Every x value is allowed. X values less than 1 and any x values starting at 1 and to the right. So that domain is any real number for x, negative infinity to positive infinity. They're all fair inputs. For the range, though, are there any outputs? Are there any y values which never get hit in our graph or thinking through our equations? Well, if you think about it, when you go to the absolute value graph, you're going to be allowed as you go to the left forever to go up forever. So we see that up forever is definitely allowed. But we do have a lowest point, don't we? A lowest y value. And that is where we have that v taking its turn, right, at the origin. So this lowest point right there, that low point, or right here, was our origin. That was at 0, 0. So if that's our lowest point at 0, 0, then that means that's our lowest y value that we do exist at. So I would put bracket 0 for my range. And how high can I go? Well, this is where you have to think a little bit. We know that to the left, we go up forever. And we know that for the parabola, going to the right, we eventually go up forever. But are there any y values that never get hit in between? Maybe at that jump discontinuity. You might think, yes, there's a jump. I see a jump, therefore, there is some values that don't get hit. However, if you notice, though, those values that would potentially not be reached between those y values where you have the hole and where you start again, okay, they actually do get reached on the other side right here when we have our absolute value piece. So you are actually reaching every y value, which means, above 0 rather, which means you are allowed to go up forever with parentheses. So that's kind of a tricky one. Really understanding the graph is critical there to get that part right. All right, I think we have one more example. Let's see if maybe, again, you can pause it and try it on your own and then come back and meet me. Our last example, going here to our next slide. Example 4, it says g of x equals 1 over x whenever x is greater than or equal to 2, and again, x whenever x is less than 2. All right, well, for those, one of those looks very familiar, I hope. The second piece, right? That second piece is a line with a slope again of 1 and a y-intercept again of 0. But that line is only allowed to exist when x is less than 2. Okay, so we'll have to be very careful there. At x equals 2, that's where the change is potentially taking place. Okay, so we have a line there. We could draw that second piece first if you feel more comfortable. That's usually my advice to students, is draw the piece that you feel most comfortable with first. So you think, oh, I love lines. I'm going to graph my line part first. Go for it. Okay. So what would I do? I would start actually at 2, potentially, because I know that's where the change is going to happen. And I would say, okay, I know x can't equal 2 for the second piece, but what would it have been if it was allowed to exist there? So at 2 itself, we would have the x value 2 in that piece, wouldn't we? That means the y value would be 2. In other words, what I'm saying is g of 2 is what? It's 2. Okay? Following our second piece's function or rule. So when x is 2, we would have been at 2. So we would have been here. Now I say would have been because it doesn't actually exist, right? This is our boundary point. So this is just for our boundary point. That's what I'm doing here. I don't want to overly confuse anyone. So for our boundary, for our open circle, I'm saying what would it have been? It would have been 2. So when x is 2, I would have had a y value at 2. So that would have been like an open circle there. Okay. Then I would have used my slope to continue for any x value below 2. So I could go to 0, and I already know that 0, I'm at 0 because my y-intercept was 0. So that would be like right there. Okay. And then if I continued going down 1 and left 1, down 1 and left 1, I'd get another point there, and I'd end up with my line looking something like this. So make sure that you have your slope of 1. So down 1, left 1, down 1, left 1. Now the second piece is actually one on top here. Let's switch to another color here. How about red? For the second piece, this was another one of those basic functions that we needed to remember. And this one was called our reciprocal function. It's one of our special rational functions, which we will study further or review further in this class. And for that one, anytime we had the graph y equals 1 over x, our reciprocal function, remember what that looks like. There is one problematic zone in that graph, and that is whenever your denominator equals 0. Okay, that's a big problem because it's undefined. You can't divide by 0. So what ends up happening at that value, that location, is you have an untouchable spot that breaks the graph into 2 pieces. And the first piece, if you were to say on the right, it would look something like this, above the x-axis and to the right of the y-axis. In other words, in quadrant 1. And the second piece would be in quadrant 3, like this. Now, I'm not making this up. This is actually the result of plotting x values, right? So for example, some easy values that you could do for this graph, you could say what's happening when x is 1, assuming that that was allowed to exist. I know that we have to look at our piece in a second, and we will go back to that. But assuming for the graph 1 over x, it was all allowed to exist, what would some easy points have been? When x is equal to 1, we would have 1 over x, where x is 1, and 1 over 1 is just 1. So that would have been like this point here. Another point, though, we could have gotten, if we were looking at the entire graph of it, would be when x is 2. 1 over 2 would be our y value then, 1/2, which would have been a little lower. So it will start to make sense why this is your shape. Why does it shoot up, going up forever as x approaches 0 from the right? Well, that's because you're saying 1 over tiny fractions. If you have 1 over 1/2, for example, that becomes 1 times 2, which is 2, because you multiply by the reciprocal. So that's why you're shooting up in y values as your x values are approaching 0 from the right. So this graph will make sense the more points you plot. So I do recommend, if you're not familiar or you think it's a little rusty, that you go back and look up reciprocal functions. Okay? So what are we going to do? We're going to take that function and we're only going to graph the piece that we're allowed to. And that is the piece when x is 2 or higher. So I already have one of those points we talked about. When x equals 2, we should be at 1/2. So at 2, we should be at 1/2. Well, that's going to be really low way down here somewhere. Okay. What about when x is 3? Because we need values bigger than 2, right? Well, wouldn't that be at 1/3? Y is 1 over x, so 1 over 3. Well, that's going to be even lower. And so what ends up happening for this piece is we get something, looks something like this. Again, I'll come to the side here and show you what I'm saying. You have a line going through the origin until you get to the x value of 2. And you have the y value there of 2 as well. So that's going to be up here with an open circle. Something like that's going on. But then when you get down to 2 for going the other direction, we're going to have the 1/2 down here, And then for 3, the 1/3 down here. And this graph is going to look something like this. So that part is where we stop. So it's harder to show when you have it really packed together like I do. But if you actually go in all of these slides, you'll notice there's a link on your PowerPoints that's interactive that says Desmos graph. What I would encourage you to do is to play with that. Click on those links on your own. You'll see the graphs zoom in and zoom out as much as you want to get a really nice feel for what's happening. But here we're just drawing sketches. So it's okay when you're drawing a sketch for things to look a little bit crazy like I'm doing right now. Okay. As long as you get the basic idea of what's happening. All right, so what is the domain here? The domain would be all x values, which again are allowed to be put in as our input. And again, the reason I'm going to say negative infinity to infinity, one more time, we've done that in all of our problems today, is because every x value is allowed to be put in. You notice that in your rules, you have when x is greater than or equal to 2, and then when x is less than 2. But 2 is allowed, and every value left and right of 2 is allowed. So that is why negative infinity to infinity. You can see that in the graph as well. It goes left forever and right forever. For the range, however, we do want to look at our graph to see what's going on. Can I go down forever? Well, definitely. As I go looking at the linear piece, the piece that's going to the left with a slope of 1, that is definitely going down forever. So we would notice that the range is negative infinity. But what about the lowest part of the range, I should say? What about the highest part of the range? Again, the question to ask here is, are you allowed to continue growing forever, or is there any values that you're skipping? So when I look at the linear piece, I notice that I continue growing until I get to the y value of 2, right? It would have been 2, we said, for that boundary. So we continue growing until we get to that location there, right? And that looks like my highest value. Why do I say that? Because the second piece is below that and continues dropping lower and lower, approaching the x-axis. There's actually an asymptote there. We'll talk about horizontal asymptotes some more in the future. So in this case, yes, the highest y value would have been 2, but it wasn't allowed to exist there. So that's a boundary, an open circle, meaning I would put 2 in parentheses there. So negative infinity to 2 with parentheses would be my range. All right, I think that's all we have for today in this piecewise functions material. So again, if any of this seemed overwhelming, make sure you go back and look at library of functions and learn those key points for each of those graphs. We'll be playing with those going forward in all of your math classes, so it's important that you really know those well. Good luck, happy practicing. Remember, math is not a spectator sport.